Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, maybe your mind is still buzzing with thoughts, or maybe you're simply someone who finds peace in the mysteries of the ocean. Whatever brought you here, you've arrived at the right place. Tonight we're going to drift together through one of the ocean's most gentle yet powerful phenomena, its currents. You don't need to do anything but rest. Let your breathing slow, your muscles soften, and your mind settle like sand after a wave. Tonight isn't about learning facts you need to remember. It's about letting the rhythm of the ocean's movement carry you into sleep, about understanding just enough to feel connected to something vast and timeless, something that has been flowing long before you were born and will continue long after. We're going to explore the invisible rivers that flow through the seas, the slow waltz of warm and cold water across thousands of miles, and the gentle forces that keep our oceans in constant, patient motion. Some of what you hear tonight might surprise you. Most of it will simply wash over you like a gentle tide, carrying you closer and closer to rest. And before we begin our journey, if these calm explorations help you unwind at the end of your day, consider liking this video and subscribing to Deep Sleep Seas. It helps others find their way here too, one peaceful soul at a time. Now let your eyes grow heavy, your breath deepen, and let's drift together into the world of ocean currents. The invisible rivers beneath the waves. Imagine for a moment that you could see the ocean not as a single body of water, but as thousands of rivers flowing through and beneath and across each other. Some moving quickly along the surface, catching the wind, others flowing deep below, so slowly that a single drop of water might take 1,000 years to complete its journey. These are ocean currents, and they are one of the most beautiful, constant features of our planet. Ocean currents are like the circulatory system of the Earth. Just as your blood moves through your body, carrying warmth and nutrients to every corner, ocean currents move water around the globe, transporting heat from the tropics to the poles, carrying nutrients from the depths to the surface, and connecting distant shores in an endless, patient circulation. Right now, as you lie here listening, millions upon millions of gallons of water are flowing through these currents. In the Atlantic, warm water is streaming northward from the tropics. In the Pacific, cold water is welling up from the depths along distant coasts. Around Antarctica, the mightiest current on Earth is circling the continent in an endless loop, connecting the world's oceans in its path. And in the deepest parts of the ocean, water that sank near Greenland centuries ago is still making its slow journey through the darkness. These currents don't rush, they don't hurry. They simply flow day after day, year after year, century after century, driven by forces so fundamental that they will continue as long as the sun shines and the earth spins. There is something deeply calming about this constancy, about knowing that no matter what happens in our brief lives, these great rivers of the sea will keep flowing, patient and eternal. Some currents are warm, carrying tropical heat toward colder regions. Others are cold, bringing frigid water from polar regions toward the equator. Some flow along the surface, pushed by winds and shaped by the Earth's rotation. Others flow along the ocean floor, moving through darkness that has never seen sunlight, driven by differences in temperature and saltiness that make water heavy enough to sink. The beauty of ocean currents is that they're invisible to us standing on shore, yet they shape everything. They determine which coasts are warm and which are cold, where fish will gather and where deserts will form on land nearby. They influence the weather you experience, the temperature of the water if you swim, even the route ships take when crossing the sea. They are everywhere and nowhere, obvious and hidden, powerful and gentle all at once. Tonight we're going to explore these currents not as a scientist would, with measurements and instruments, but as a dreamer would, with wonder and peace. We'll travel from the surface to the depths, from the tropics to the poles, following water on journeys that span oceans and centuries. And as we do, let yourself imagine the scale of it all, the vastness of these flows, the patience of water that moves so slowly you could never see it, yet never stops moving. Deep beneath the surface of the ocean, something remarkable is happening. Water that cooled near Greenland is sinking toward the ocean floor and beginning a journey that will take it through all the world's oceans. This is the start of what scientists call the thermohaline circulation, but you might know it by its more poetic name, the Great Ocean Conveyor Belt. The word thermohaline comes from two Greek words. Thermo means heat, and haline means salt. Together they describe the two forces that drive this deep circulation, temperature and salinity. These are the twin engines of the ocean's deepest currents, working together in a slow but constant dance that has been going on for millions of years. Here's how it works, and it's wonderfully simple. Water becomes denser or heavier when it gets colder or when it gets saltier. Imagine a glass of warm water and a glass of cold water. If you could somehow stack them perfectly, the cold water would sink below the warm water because it's heavier. The same thing happens in the ocean, but on an enormous scale. In the North Atlantic Ocean, something magical happens every winter. Warm water flows northward from the tropics, carried by surface currents we'll talk about soon. As this water moves into the cold regions near Greenland and Iceland, it begins to cool. The frigid air above the ocean pulls heat from the water, and as autumn turns to winter, the surface water grows colder and colder. But something else happens too. Some of this water freezes, forming sea ice. When seawater freezes, it leaves most of its salt behind. The salt doesn't fit into the structure of ice, so it gets pushed into the liquid water below. This makes the remaining water saltier, and saltier water is heavier water. Now you have water that is both very cold and very salty. It becomes so dense, so heavy, that it can no longer stay at the surface. Slowly, gently, it begins to sink. Down it goes, through the layers of the ocean, until it reaches the ocean floor, and once it's down there, it begins to flow. This deep water doesn't just sit at the bottom. It starts moving, pushed and pulled by the very subtle pressure differences created by more water sinking behind it. It flows south through the Atlantic, hugging the western boundary of the ocean basin. It moves slowly, extraordinarily slowly by our standards. While a surface current might flow at several miles per hour, this deep current moves at perhaps 1 centimeter per second. That's about half a mile per day. Slow, patient, unhurried. As this deep water flows south through the Atlantic, it meets water that sank near Antarctica. The Antarctic contributes its own deep water, water that sank in the brutally cold seas around that frozen continent. Together, these water masses, now called North Atlantic deep water and Antarctic bottom water, continue their journey. They flow eastward around Africa, pushed by the geography of the ocean floor and the currents above. Some of this water moves into the Indian Ocean. Some continues into the Pacific. In both oceans, it spreads out, flowing along the bottom, gradually mixing with the water above it, but maintaining its identity as cold, deep water that came from the poles. And it keeps moving through the Indian Ocean, through the Pacific, always eastward, always slowly, never stopping. Scientists estimate that it takes this water somewhere between 1,000 and 2,000 years to complete its journey through the ocean basins. Think about that for a moment. Water that sank near Greenland when the Roman Empire was at its height might only now be welling up somewhere in the North Pacific. Water that sank during the Middle Ages might still be flowing through the Indian Ocean, far from sunlight, far from warmth, patient in its journey. Eventually, this deep water does return to the surface. In parts of the Southern Ocean, and in regions of the Pacific far from where the water originally sank, the deep water slowly upwells, rising through the layers of the ocean until it reaches the surface again. There, warmed by the sun and freshened by rain, it begins to flow back across the surface, completing the great circulation. Surface water flows toward the poles, cools, sinks, flows through the depths, rises, and begins again. This conveyor belt never stops. Day and night, summer and winter. It continues its slow circulation. It connects all the world's ocean basins into one vast system. It carries heat from the tropics toward the poles, helping to moderate Earth's temperature. It carries oxygen from the surface into the depths, sustaining life in the darkest parts of the ocean. It mixes the ocean vertically, preventing the water from becoming too stratified, too separated into layers that never mix. The thermohaline circulation is driven by forces that are beyond human control. As long as the sun heats the equator more than the poles, as long as ice forms and melts, as long as evaporation and rain alter the saltiness of seawater, this circulation will continue. It is one of the fundamental processes of our planet, a slow pulse that has been beating since the oceans formed. There's something deeply restful about imagining this circulation, about knowing that right now, somewhere in the North Atlantic, cold water is sinking into darkness to begin a journey that will last centuries. About knowing that in the Pacific, ancient water is rising, finally returning to the surface after a 1,000-year voyage. The scale is so vast, the movement so slow that it puts our own hurried lives into perspective. The ocean has time, the ocean has patience, and tonight, as you drift towards sleep, perhaps you can borrow a little of that patience for yourself. If the thermohaline circulation is the ocean's slow, deep pulse, then the Gulf Stream is its racing heartbeat. This is a current you could almost believe in if you saw it from space, a river of warm water flowing through the cooler Atlantic, so distinct that you can see the boundary where its deep blue meets the green-gray waters on either side. The Gulf Stream begins its life in the warm waters of the Gulf of Mexico and the Caribbean Sea. Picture the tropical sun beating down on shallow seas, heating the water to temperatures that would feel like a warm bath. Trade winds push this water westward, piling it up against the coasts of Central America and the Yucatan Peninsula. With nowhere else to go, the water flows northward through the narrow straits of Florida, squeezed between Florida and Cuba. This squeezing, this narrowing of the passage, does something remarkable. It accelerates the current. Like putting your thumb over the end of a garden hose, narrowing the channel makes the water flow faster. By the time the Gulf Stream exits the Straits of Florida, it's moving at speeds that would impress you if you could see it. The maximum speed near the surface is typically about 2.5 meters per second, which translates to about 9 kilometers per hour or 5.5 miles per hour. The average speed is still a respectable 4 miles per hour. Now that might not sound terribly fast. You could walk faster than that. But remember, this isn't a person walking or a car driving. This is an entire river of water, flowing through the ocean, and it's carrying an almost unimaginable volume. Scientists estimate that the Gulf Stream transports about 30 million cubic meters of water every second. That's more than 100 times the combined flow of all the rivers on Earth. Every second, hour after hour, day after day, year after year. As the Gulf Stream flows northward along the eastern coast of the United States, it continues to carry its cargo of warm water. The current is typically about 100 kilometers wide and extends downward 800 to 1200 meters. That's about half a mile deep. Imagine a river of warm water, 60 miles wide and half a mile deep, flowing past the coast at several miles per hour. The mind can barely grasp the scale. This warm water has profound effects on everything around it. Along the coast of Florida, the Gulf Stream helps keep temperatures mild, warmer in winter, and slightly cooler in summer than they would otherwise be. The warm water evaporates readily, putting moisture into the air, which influences rainfall patterns across the region. Tropical fish and organisms that normally couldn't survive at these latitudes ride the Gulf Stream northward, some making it all the way to Massachusetts during summer before turning back as winter approaches. The Gulf Stream also influences weather in ways that are sometimes dramatic. The warm water is a source of heat and moisture for the atmosphere above it. Hurricanes that pass over the Gulf Stream can intensify rapidly, drawing energy from the warm water like fuel for an engine. The difference in temperature between the Gulf Stream and the surrounding water can create zones where storms deepen and strengthen, affecting coastal communities. Around Cape Hatteras, North Carolina, at about 36 degrees north latitude, something interesting happens. The Gulf Stream begins to leave the coast, veering away from the shoreline and heading out into the open Atlantic. No longer constrained by the continental margin, it broadens and slows slightly, but it continues its northeastern journey across the ocean. As it crosses the Atlantic, the Gulf Stream becomes broader and more diffuse, eventually splitting into several branches. The northern branch, called the North Atlantic Current or North Atlantic Drift, continues toward northern Europe. This is where the Gulf Stream's influence on climate becomes most dramatic. Without the Gulf Stream and its extension, the North Atlantic Current, Europe would be a much colder place. The current carries an enormous amount of heat northward, heat that it releases into the air as it flows. This warm air then influences weather patterns across Western Europe. England, Ireland, Norway, even parts of the Arctic experience temperatures much warmer than you'd expect for their latitude. London, for example, is at about the same latitude as Calgary, Canada, which experiences harsh winters. But London rarely sees heavy snow, and its winters are relatively mild. The Gulf Stream, bringing warmth from the tropics, makes the difference. The southern branch of the Gulf Stream recirculates back toward Africa, eventually becoming part of the Canary Current that flows south along the African coast. And so the water that started in the Caribbean completes a great circuit of the North Atlantic, part of one of the ocean's major gyres. Scientists have studied the Gulf Stream for centuries. Benjamin Franklin in the 1700s was one of the first to map it, recognizing that ships sailing from America to Europe could save time by staying in the current, while ships sailing the other way should avoid it. In the centuries since, we've learned much more, but the Gulf Stream remains a subject of intense study, particularly as climate changes and scientists work to understand how this crucial current might be affected. Recent research suggests the Gulf Stream is warming faster than the global ocean average, and may be shifting slightly closer to the coast in some regions. The current has weakened and strengthened over the decades, responding to complex changes in wind patterns, water temperatures, and the overall circulation of the Atlantic. But through all these changes, the Gulf Stream continues its northward flow, a massive river in the ocean, carrying warmth and life from the tropics toward the poles. There's something almost alive about the Gulf Stream, something dynamic and present. It's not just water moving from one place to another. It's a phenomenon that connects distant places, that makes certain coastlines habitable and others cold, that influences the lives of millions of people and billions of sea creatures. And it does all this through the simple, elegant mechanism of warm water flowing through cooler water, driven by winds and the rotation of the Earth, sustained by the heat of the sun. As you rest here tonight, imagine that river in the ocean. Picture it from above if you can. See its deep blue cutting through the grey-green Atlantic, carrying its warmth northward, flowing and flowing, never stopping, patient and powerful at once. Let the rhythm of that flow, the constancy of it, help carry you towards sleep. Not all ocean currents are driven by differences in temperature and salt. Some of the most visible and important currents are pushed by something we can all understand: wind. These are the surface currents, the movements of water in the upper few hundred meters of the ocean, and they paint great swirls across the ocean basins, driven by the winds and shaped by the rotation of the Earth itself. Wind moving across the surface of the ocean does something that seems simple but creates complex patterns. When wind blows across water, it drags the surface along with it through friction. The air molecules moving over the water pull on the water molecules, and the water begins to move in the direction the wind is blowing. This is wind stress, and it's the primary driver of surface ocean currents. But here's where it gets interesting, where the simple becomes complex and beautiful. The water doesn't move exactly in the direction the wind blows. Instead, it moves at an angle, deflected by a force that seems almost magical if you don't know its cause. This is the Coriolis effect, and it's one of the most fundamental influences on ocean currents, on weather patterns, on the movement of anything that travels long distances across the surface of our planet. The Coriolis effect exists because the Earth is round and spinning. Imagine you're standing at the equator. The equator is the widest part of the Earth, about 40,000 kilometers around, and every point on it has to complete a full rotation in 24 hours. That means you're moving east at about 1,600 kilometers per hour. Even though you're standing still, you don't feel it because everything around you, the air, the water, the ground, is all moving at the same speed. Now imagine you're standing at the North Pole. Here you're standing on the axis of Earth's rotation. You're spinning in a circle, but you're not actually moving east or west at all. Your speed relative to the stars is essentially zero. Between the equator and the poles, different latitudes move at different speeds. At 30 degrees latitude, the rotational speed is about 1,400 kilometers per hour. At 60 degrees, it's about 800 kilometers per hour. This difference in speed, this gradient from fast at the equator to slow at the poles, is what creates the Coriolis effect. When something moves north or south across these changing speeds, it carries its original eastward or westward momentum with it. A mass of air or water moving north from the equator is moving east at 1,600 kilometers per hour. As it travels north, it moves over ground that's rotating more slowly, so the moving air or water appears to curve ahead of the surface beneath it. To someone standing on that surface, watching the movement, it looks like the air or water is curving to the right. Similarly, something moving south from high latitudes is moving slowly to the east. As it moves over faster moving ground nearer the equator, it appears to curve behind, which also looks like curving to the right from the perspective of someone in the northern hemisphere. In the southern hemisphere, the effect is reversed. Moving objects appear to curve to the left. This deflection, this curving of moving water and air, shapes the entire pattern of surface ocean currents. Winds don't blow straight from high pressure to low pressure. They curve. Water driven by those winds doesn't flow straight with the wind. It curves. And the result is the great circular patterns we see in every ocean basin, the ocean gyres. Look at any major ocean, and you'll see these gyres. In the North Atlantic, water flows westward along the equator as part of the North Equatorial Current. When it reaches the Americas, it flows north along the coast, becoming the Gulf Stream. The Gulf Stream crosses the Atlantic to Europe, where it becomes the North Atlantic Current. Some of that water flows into the Nordic seas, but much of it turns south, becoming the Canary Current along the African coast. The Canary Current flows back toward the equator, completing the circuit. This is the North Atlantic Gyre, a huge circular flow of water rotating clockwise when viewed from above. And it exists because of the winds, the Coriolis effect, and the positions of the continents that help channel the flow. The South Atlantic has its own gyre, rotating counterclockwise. The Pacific has two major gyres in each hemisphere. The Indian Ocean has its own complex circulation. All of them are created by the same simple forces, wind and the Earth's rotation. The Coriolis effect does something else interesting to surface currents. When wind blows across the ocean, the surface water doesn't just move in the direction of the wind, it moves at an angle to the wind, deflected by the Coriolis effect. In the northern hemisphere, surface water moves about 45 degrees to the right of the wind direction. In the southern hemisphere, 45 degrees to the left. But the effect doesn't stop at the surface. The moving surface water drags on the water just below it, which begins to move as well. But this deeper water is also deflected by the Coriolis effect, moving at an angle to the water above it. Layer by layer, as you go deeper, each layer of water moves at an angle to the one above, and each layer moves a bit more slowly because it's farther from the direct influence of the wind. The result is a spiral. The surface moves in one direction, the water just below moves at an angle, the water below that at a further angle, and so on, creating a spiral pattern through the water column. This is called the Ekman spiral, named after the Swedish oceanographer who first described it. By the time you go down about 100 meters, the water is moving in the opposite direction from the surface, though very slowly. This Ekman transport, the net movement of water caused by wind, has important consequences. Along coastlines where winds blow parallel to the shore, the Ekman transport can move water either toward or away from the coast. When it moves water away from the coast, deeper water rises to replace it in a process we'll explore soon, bringing cold, nutrient-rich water to the surface. When it moves water toward the coast, surface water piles up and sinks, carrying oxygen downward. The beauty of wind-driven currents is their responsiveness. Unlike the deep thermohaline circulation that takes centuries to complete a loop, surface currents respond to the winds within days or weeks. When wind patterns change with the seasons, surface currents adjust. When a strong storm passes over the ocean, it can create currents and turbulence that persist for days afterward. There's an immediacy to these surface flows, a connection to the atmosphere above that makes them dynamic and ever-changing. Yet even with their changeability, these currents follow patterns. The trade winds blow steadily across the tropical oceans, pushing water westward. The westerlies blow across the temperate latitudes, pushing water eastward. The polar easterlies complete the pattern at high latitudes, and the ocean responds, creating the gyres, the currents, the swirls and eddies that transport heat and nutrients and life across the ocean basins. As you lie here, imagine the wind blowing across the open ocean. Feel it in your imagination, the steady push of air against water. Watch the surface begin to move, water flowing with the wind but curving gently to the side. See layer upon layer beneath the surface, joining the movement, each at its own angle, creating a spiral of motion through the water. This is how the ocean breathes, how it responds to the atmosphere, how it stays in constant gentle motion even when nothing seems to be happening. Let that gentle, constant motion carry you deeper into rest. Far to the south, in the cold waters surrounding Antarctica, there flows a current unlike any other on Earth. It is the strongest current on the planet, the longest and in many ways the most important. This is the Antarctic Circumpolar Current, and it is the only ocean current that flows completely around the globe with no land to block its path. The Antarctic Circumpolar Current exists because of a unique circumstance of geography. Antarctica sits at the South Pole, surrounded entirely by ocean. There are no continents connecting to it, no land bridges, nothing to block the flow of water around it. This means that between the southern tips of South America, Africa, and Australia, and the coast of Antarctica itself, there is open ocean all the way around the world. Into this gap blow the powerful westerly winds of the Southern Ocean, the infamous winds that sailors have called the Roaring Forties, the Furious 50s, and the Screaming 60s, named after the latitudes where they blow. These winds are among the strongest and most consistent on Earth, and they push enormous quantities of water eastward, around and around Antarctica, in an endless circulation. The scale of the Antarctic circumpolar current is difficult to comprehend. Scientists estimate that it transports somewhere between 135 and 150 million cubic meters of water every second. That's not a misprint. Every second, an amount of water equal to the volume of more than 100 times all the rivers on Earth flows through this current. It is by far the largest movement of water on the planet. The current is not a simple stream. It's actually made up of multiple jets, filaments of faster flow, embedded in the broader eastward movement. These jets meander like a river wandering across a floodplain, sometimes moving north, sometimes south, creating intricate patterns of flow. Between and around these jets are eddies, swirling masses of water that can be hundreds of kilometers across, spinning off from the main current and drifting away, carrying water and heat and nutrients with them. The Antarctic circumpolar current flows at an average speed of about 4 kilometers per hour, over the relatively shallow Macquarie Ridge south of New Zealand. That might not sound fast, but remember the volume, 4 kilometers per hour, times 140 million cubic meters per second, equals an almost unimaginable amount of water in motion. This current serves several crucial functions in the Earth's climate system. First and most obviously, it connects the three major ocean basins, the Atlantic, Pacific, and Indian Oceans. Water that flows out of the Atlantic into the Southern Ocean can continue into either the Indian or Pacific. Water from the Pacific can flow into the Indian or Atlantic. The Antarctic circumpolar current is the primary means by which these ocean basins exchange water and everything water carries: heat, salt, nutrients, dissolved gases, even microscopic organisms. Second, the current acts as a barrier, keeping warm subtropical water away from Antarctica. The flow is so strong and continuous that it's difficult for warm water from the north to cross it and reach the Antarctic coast. This helps maintain Antarctica's cold temperatures and massive ice sheets. Without the Antarctic circumpolar current, warm water would more easily reach the continent, potentially causing more melting and dramatically altering Antarctica's ice dynamics. Third, the current plays a vital role in the global overturning circulation we discussed earlier. In the Southern Ocean, deep water that has been flowing through the ocean basins for centuries finally rises back toward the surface. This upwelling is driven partly by the strong winds and partly by the geography of the ocean floor. Once at the surface, some of this water flows northward into the Atlantic, Pacific, and Indian Oceans, while some flows southward toward Antarctica, where it cools, sinks, and becomes Antarctic bottom water. The Antarctic circumpolar current also supports remarkable biodiversity, despite the harsh conditions. The upwelling of deep water brings nutrients to the surface, and where nutrients and sunlight meet, phytoplankton bloom. These microscopic plants form the base of a food web that supports huge populations of krill, small shrimp-like creatures that are in turn eaten by fish, seals, penguins, and the great baleen whales. Some of the most productive marine ecosystems on Earth exist in the waters of the Antarctic circumpolar current. Scientists study this current intensively, in part because it's changing. As the climate warms, the westerly winds that drive the current are intensifying, and the current appears to be accelerating. Observations over the past decades show that the flow is getting faster, particularly along certain jets within the current. This has implications for how heat moves through the global ocean, how carbon dioxide is absorbed by the ocean, and how Antarctic ice responds to changing ocean conditions. The current also appears to be shifting position slightly, sometimes moving north, sometimes south, in response to changes in wind patterns and ocean temperatures. These shifts can affect regional climate in South America, Southern Africa, Australia, and New Zealand, changing rainfall patterns and storm tracks. There's something almost hypnotic about imagining this current, about picturing water flowing endlessly around the bottom of the world. driven by relentless winds, never blocked, never stopped, just flowing and flowing in a circle that takes it through all longitudes, through all time zones, connecting all oceans in its path. It flows now as it has flowed for millions of years, and as it will continue to flow for millions more, as long as Antarctica sits at the pole and winds blow across the Southern Ocean. As you rest here tonight, imagine that flow. Picture the cold water moving endlessly eastward, pushed by winds that never stop blowing. Imagine the scale of it, the power, yet the patience. There's no hurry in the Antarctic circumpolar current. It's not rushing to get anywhere. It's already everywhere, encircling a continent, connecting oceans, flowing in an eternal loop. Let the endlessness of that flow, the circularity of it, settle your mind. Let yourself flow with it, around and around, until the circles of thought and worry fade and you drift into sleep. Beneath the surface of the ocean, in the deep, cold waters where sunlight never reaches, there are nutrients, nitrogen, phosphorus, iron, silicate, all the chemical elements that tiny plants need to grow. These nutrients accumulate in the deep, because when organisms die, their remains sink, decomposing as they fall, releasing their constituent chemicals into the water. Over time, over centuries, the deep ocean becomes rich in these nutrients while the surface waters, where all the sunlight is, become depleted. The plants use up the nutrients as fast as they're supplied, and there's no easy way for more nutrients to get from the deep to the surface. Except there is. There's a process, gentle and inexorable, that brings deep water to the surface, delivering those nutrients where they're needed. This process is called upwelling, and it's one of the most important phenomena in the ocean for supporting life. Upwelling occurs in several ways and in several places, but the most dramatic and important is coastal upwelling along certain shorelines. Imagine a coastline running north-south, and imagine winds blowing along that coast from north to south. Because of the Coriolis effect we discussed earlier, the surface water moved by those winds doesn't flow straight south with the wind. In the northern hemisphere, it flows to the right of the wind, which means offshore, away from the coast. As surface water moves offshore, it has to be replaced by something. Nature abhors a vacuum, even an underwater one. The water that rises to replace the offshore moving surface water comes from below. It wells up from the depths, bringing with it the cold and the nutrients that have been accumulating there. This upwelled water is strikingly different from the water it replaces. It's much colder, sometimes 10 or 15 degrees colder than the surrounding surface water. You can see the boundary from space as a change in color. The upwelled water often appears darker, greener, because it quickly becomes rich in phytoplankton that bloom in response to the nutrients. The most productive marine ecosystems on Earth are found in upwelling zones. Along the west coasts of continents, where upwelling is most common, the ocean teems with life. The California Current along the western United States, the Humboldt Current along western South America, the Benguela Current along southwestern Africa, and the Canary Current along northwestern Africa, all feature strong upwelling. Together, these four eastern boundary current systems account for about 20% of the global marine fish catch, despite covering only about 1% of the ocean's surface. The productivity in upwelling zones is almost unimaginable. The nutrients brought from depth fuel enormous blooms of phytoplankton, microscopic plants that can turn the water so green and thick that it looks like pea soup. These phytoplankton are eaten by zooplankton, tiny animals that in turn are eaten by small fish. The small fish are eaten by larger fish, and by seabirds, and by marine mammals. Seals, sea lions, dolphins, whales all gather in upwelling zones to feast on the abundance. The fishing industries of several nations depend entirely on upwelling zones. Peru's anchovy fishery, one of the largest in the world, exists because of the upwelling along its coast. The California sardine fishery was once enormous before overfishing depleted the stocks. Upwelling zones are literally where the ocean's nutrients are brought to the surface and converted into life, and humans have learned to harvest that life. But upwelling isn't just about nutrients and fish. It also affects climate. The cold water brought to the surface cools the air above it, which can create fog and affect precipitation patterns on nearby land. Much of the western coast of continents, where upwelling occurs, is remarkably dry despite being right next to the ocean. This is because the cold water cools the air to the point where it can't hold much moisture. and it also creates temperature inversions that prevent clouds from forming. Some of the driest deserts on Earth, like the Atacama in Chile and the Namib in southwestern Africa, exist right next to upwelling zones. Upwelling also occurs in the open ocean, away from coasts. At the equator, the Coriolis effect causes water north of the equator to move slightly north, and water south of the equator to move slightly north, and water south of the equator to move slightly south, creating a divergence right at the equator. Water wells up from below to replace the diverging surface water, creating a band of cool, productive water right along the equator, particularly in the Pacific. The Southern Ocean around Antarctica also features strong upwelling, though it works differently than coastal upwelling. Here, the powerful winds of the westerlies create a zone where deep water is literally sucked toward the surface, bringing ancient water that sank in the North Atlantic centuries ago finally back into contact with the atmosphere. Upwelling zones are dynamic, responding to changes in wind patterns. During El Niño events in the Pacific, for example, the normal trade winds weaken, and the upwelling along the South American coast weakens or stops. The lack of nutrients causes fisheries to collapse temporarily, and the warm water that remains at the surface affects weather patterns around the world. When the winds return to normal, upwelling resumes, and the ecosystem recovers. There's something almost generous about upwelling, about the way the ocean brings nutrients from its depths to its surface, supporting life, feeding billions of organisms from the smallest plankton to the largest whales. It's a circulation within the circulation, a vertical mixing that complements the horizontal currents, ensuring that the resources of the deep aren't locked away forever, but are continuously recycled to where they're needed. As you drift here tonight, imagine that upwelling. Picture cold water, dark water, water that has been in the depths for perhaps years or decades, slowly rising toward the light. Imagine it breaking the surface, spreading out, blooming with life as microscopic plants suddenly have access to both nutrients and sunlight. Imagine the abundance that follows, the fish gathering, the birds diving, the whole ecosystem responding to this gift from the depths. The ocean provides, the ocean gives, and it does so through this simple, elegant process of water rising from below. Every day, twice a day in most places, the ocean rises and falls. The tide comes in, flooding beaches, filling estuaries, lifting boats in harbors. Then it goes out, draining away, exposing mudflats and tide pools, grounding boats that weren't properly moored. This rhythm has been going on for as long as there has been an ocean and a moon, and it creates currents, tidal currents, that are different from any we've discussed so far. Tidal currents are the horizontal movement of water caused by the rising and falling of the tides. When the tide comes in, water flows toward the shore, into bays and estuaries, upstream in tidal rivers. When the tide goes out, water flows back toward the ocean. These flows can be surprisingly strong in narrow channels, sometimes creating currents of several knots, strong enough to challenge even experienced sailors and to create whirlpools and standing waves where the current is forced through narrow passages. The tides themselves are caused by the gravitational pull of the moon, and to a lesser extent, the sun. The moon pulls on the Earth, and because the ocean is liquid, it responds to that pull by bulging slightly toward the moon. But interestingly, there's also a bulge on the opposite side of the Earth, away from the moon. This happens because the moon isn't pulling equally on all parts of the Earth. It pulls strongest on the side closest to it, less strongly on the center of the Earth, and least strongly on the far side. The differences in gravitational force create two bulges in the ocean, one toward the moon and one away from it. As the Earth rotates, these bulges stay roughly aligned with the moon. So from the perspective of someone standing on the shore, it looks like the bulges are moving around the Earth. First one bulge passes, creating high tide. Roughly 12 hours later, as the Earth continues to rotate, the second bulge passes, creating another high tide. In between are the low tides. The sun also creates tidal bulges, but because it's so much farther away, its effect is smaller, about half the size of the moon's effect. However, when the sun, moon, and Earth line up, either at new moon or full moon, their gravitational effects add together, creating particularly high tides and particularly low tides. These are called spring tides, not because they occur in spring, but from an old word meaning to spring up. When the sun and moon are at right angles to each other, at first quarter or third quarter moon, their effects partially cancel, creating smaller tidal ranges called neap tides. The tidal currents that result from these tides can be quite complex. In the open ocean, far from land, tidal currents are relatively weak and barely noticeable. But near coasts, particularly in narrow channels, bays and estuaries, tidal currents can become the dominant water movement, far stronger than any wind-driven or density-driven current. The period of no current between the outgoing tide and the incoming tide is called slack water. This is the moment when the tide has finished going out but hasn't yet started coming back in, or has finished coming in but hasn't yet started going out. Slack water can last just a few seconds in some places or several minutes in others. It's the time when boats can most easily navigate channels with strong tidal currents, and when divers can most safely enter the water. After slack water, the current begins to flow in the opposite direction. The incoming tide creates what's called a flood current, carrying water toward the shore. The outgoing tide creates an ebb current, carrying water away from shore. These currents gradually increase in strength, usually reaching their maximum speed, roughly midway between high and low tide, then gradually decreasing as the tide approaches its extreme and slack water occurs again. In some special places, tidal currents create remarkable phenomena. Tidal bores occur in certain rivers, where the incoming tide forms a wave that travels upstream against the river's current. The bore can be several feet high and moves at running speed, a wall of water advancing up the river. Only a few dozen rivers in the world have tidal bores, and they require specific combinations of tidal range and river geometry. In other places, strong tidal currents flowing through narrow passages create whirlpools and maelstroms. The Saltstraumen near Bodø, Norway, is considered the strongest tidal current in the world, with water flowing at speeds up to 20 knots through a narrow strait, creating vast whirlpools. The Old Sow whirlpool between Maine and New Brunswick, and the Corrie Vrecken between two Scottish islands, are other examples of the dramatic effects tidal currents can create. For most people, though, tidal currents are more subtle. They're the reason why swimming is easier at one time of day than another in certain places. They're why boats pull on their anchors first in one direction, then in the other. They're the force that slowly moves sediment along coastlines, building some beaches and eroding others, shaping the very geography of the shore. There's something profoundly ancient and rhythmic about tides and tidal currents. The moon has been pulling on Earth's oceans for billions of years. The rhythm of rise and fall, in and out, high and low, is one of the oldest rhythms on the planet. Countless organisms time their reproduction, their feeding, their movement by the tides. Coastal peoples throughout history have organized their lives around tidal rhythms, knowing when the tide would be right for fishing, for gathering shellfish, for launching boats. The tides are also slowing down Earth's rotation, very gradually. The friction of the tides moving across the ocean floor is transferring rotational energy from the Earth to the Moon, lengthening our day by about 2 milliseconds per century, and causing the Moon to slowly spiral away from Earth. Billions of years ago, when the Moon was younger and closer, the tides were much higher, and the day was much shorter. Billions of years in the future, if nothing else changes, the day will be much longer, and the tides will be smaller. But these changes happen so slowly that they're invisible to us. From our perspective, the tides are eternal, unchanging, a rhythm as reliable as breathing. Every day, the water rises and falls. Every day, tidal currents flow in and out. And every day, the Moon continues its orbit, pulling and releasing, creating these ancient movements in the ocean. As you rest here, imagine the tides. Feel the pull of the Moon, even though you can't truly feel it. Picture the water responding, rising on shores around the world, then falling again. Imagine the current flowing into a narrow bay, slack water, then the current reversing, flowing back out, in and out, like breathing, rising and falling, like your chest as you breathe. Let the rhythm of the tides match the rhythm of your breath, slow and steady, and let that rhythm carry you deeper into rest. Far beneath the surface, beyond where sunlight can reach, in the cold and dark water moves. These are the deep ocean currents, the abyssal flows, moving along the ocean floor at speeds so slow you'd never notice them, yet carrying vast amounts of water on journeys that can last centuries. We've already talked about the thermohaline circulation, the great conveyor belt that takes water from the surface to the depths and back again over the course of 1,000 years or more. But within that broad pattern, there are specific water masses, bodies of water with distinct characteristics that can be traced as they flow through the ocean basins. In the North Atlantic, the water that sinks near Greenland and Iceland becomes North Atlantic deep water. This water mass is relatively warm for deep water, staying above 2 degrees Celsius, and it's quite salty, more than 34.9 parts per thousand. As it sinks and begins its journey south along the western boundary of the Atlantic, it maintains these characteristics. Oceanographers can identify North Atlantic deep water by measuring temperature and salinity, and they can track where it goes. North Atlantic deep water flows south through the Atlantic, hugging the coasts of North and South America. It flows deep, typically between 2,000 and 4,000 meters below the surface, under the Gulf Stream and the other surface currents, largely unaffected by what's happening above. As it flows, it gradually mixes with the water around it, losing some of its distinct characteristics, but remaining identifiable for thousands of kilometers. Near Antarctica, it meets Antarctic bottom water, which is even colder and slightly less salty. Antarctic bottom water is formed in the Weddell Sea and the Ross Sea, where the most intense cooling occurs on Earth. Air temperatures in winter over these seas can drop to -40 degrees Celsius or colder, and sea ice forms rapidly. The water left behind after freezing is so cold and dense that it sinks to the very bottom of the ocean, colder than 0 degrees Celsius, just above the freezing point of seawater. This Antarctic bottom water spreads northward along the ocean floor, underneath the North Atlantic deep water. It's the densest water in the ocean, so it naturally sinks below everything else. Slowly, over decades and centuries, it creeps northward into the Atlantic, into the Indian Ocean, into the Pacific, spreading across the abyssal plains. In the Indian and Pacific Oceans, these two water masses, North Atlantic deep water and Antarctic bottom water, gradually mix together. They lose their individual identities and become what oceanographers call common water. This water continues to flow through the deep ocean, slowly upwelling in some regions, mixing with the water above, completing the great vertical circulation. The speeds of these deep currents are extraordinarily slow. While surface currents might flow at several kilometers per hour, deep currents flow at perhaps 1 or 2 centimeters per second. That's less than 1 kilometer per day. At that speed, it takes years to cross an ocean basin, decades to circle the globe. The water isn't in a hurry. It has time. Despite their slowness, deep currents are crucial for several reasons. First, they transport heat. Even though deep water is cold, it's warmer than the temperatures that would exist in the deep ocean without any circulation. The deep ocean, remember, is completely cut off from sunlight. Without circulation bringing slightly warmer water from the surface, the deep ocean would be even colder than it already is. Second, deep currents transport oxygen. The water that sinks in the North Atlantic and around Antarctica is saturated with oxygen from contact with the atmosphere. When this water sinks, it carries that oxygen into the depths. Deep sea organisms depend on this oxygen. Without the slow circulation bringing oxygenated water from the surface, the deep ocean would be anoxic, devoid of oxygen, and most life there would be impossible. Third, deep currents transport nutrients. As we discussed with upwelling, nutrients accumulate in the deep ocean as organic matter sinks and decomposes. The deep currents move these nutrients around, eventually bringing them to regions where upwelling can carry them back to the surface. Deep currents are also affected by the topography of the ocean floor. Underwater mountains, ridges, and canyons can channel, block, or redirect deep water flows. The Mid-Atlantic Ridge, for example, runs down the center of the Atlantic Ocean like an underwater mountain range. Deep water has to flow around it or through gaps in it, and this affects the pattern of circulation. The Drake Passage between South America and Antarctica is one of the few places where water can flow freely at all depths around the world, and it plays a crucial role in connecting the Atlantic with the Pacific and Indian Oceans. Studying deep currents is challenging. You can't see them from satellites. You can't observe them from ships on the surface without special instruments. For a long time, oceanographers had to infer the existence and speed of deep currents from the distribution of temperature and salinity, from the spread of chemical traces, from indirect evidence. More recently, moored instruments and autonomous floats that drift with the currents have given us direct measurements, filling in the picture of how water moves in the deep. There's something almost meditative about imagining the deep currents. Picture water moving slowly along the ocean floor, through darkness that has existed since the ocean formed, past underwater mountains and across vast plains of sediment. Nothing disturbs this water except its own slow movement and the occasional passage of a deep-sea creature. It's peaceful down there, quiet in a way that's hard to imagine. The surface may be in turmoil with storms and waves, but the deep is calm, steady, flowing. These waters have a timelessness to them. A parcel of water sinking near Greenland might not return to the surface for 1,000 years or more. Think about that. Water that sank when Europe was in the Dark Ages might still be flowing through the Pacific, only now beginning its upwelling journey back to the surface. Water sinking today might not see sunlight again until the year 3000. As you lie here tonight, imagine that slow journey. Imagine water sinking from the surface into darkness, beginning its patient flow through the ocean basins. Feel the slowness of it, the absence of hurry. There's no rushing in the deep ocean. There's only the slow, steady flow, as constant and patient as time itself. Let that slowness, that patience, that constancy settle into you. Let your thoughts slow like deep water. Let yourself sink like water, sinking into the depths, slowly, gently, peacefully, until you reach the bottom, which is sleep. In the ocean, there are invisible boundaries, places where different water masses meet and interact. These are convergence zones, and though you can't see them when you look at the ocean surface, they have profound effects on everything from nutrient distribution to weather patterns to where marine life gathers. A convergence zone forms wherever two different bodies of water meet. This might be where cold water meets warm water, where fresh water meets salty water, or where water moving in one direction meets water moving in another direction. At these boundaries, the water doesn't simply mix instantly. Instead, the differences in density, temperature, and salinity create distinct fronts, almost like walls in the water. One of the most famous convergence zones is the Antarctic Convergence, also called the Antarctic Polar Front. This is where the cold waters flowing north from around Antarctica meet the warmer subtropical waters flowing south. The boundary is remarkably sharp. You can sail through it and measure a temperature drop of several degrees within just a few kilometers. The water on the Antarctic side is cold, around 2 to 3 degrees Celsius. The water on the subtropical side might be 10 degrees warmer. At the Antarctic Convergence, the cold, denser water from the south sinks beneath the warmer water from the north. This creates a zone of mixing and upwelling, and where water from different sources meets and mixes, nutrients are brought together and productivity increases dramatically. The Antarctic Convergence is one of the most biologically productive regions in the Southern Ocean, rich in phytoplankton, krill, and the fish, seals, and whales that feed on them. Similar convergence zones exist around all the ocean gyres. At the center of each major gyre, water converges, and because there's nowhere for the converging surface water to go but down, it sinks. These are zones of downwelling, the opposite of the upwelling we discussed earlier. Downwelling zones tend to be less productive because nutrients are being carried downward rather than brought up. The Sargasso Sea in the center of the North Atlantic Gyre is an example, a region known for its clear blue water, beautiful but relatively barren because nutrients are scarce. At the edges of gyres, though, where different currents meet and interact, you often find convergence zones with upwelling and high productivity. The North Pacific Transition Zone, where the warmer waters of the Kuroshio Current extension meet the colder waters of the subarctic Pacific, is a convergence zone that shifts north and south with the seasons. When it moves, it carries fish populations with it, and commercial fisheries follow. Convergence zones can also be frontal zones associated with major currents. The boundary of the Gulf Stream, for example, is a kind of convergence zone where the warm water of the stream meets the colder coastal water. The difference in temperature can be dramatic, 10 degrees Celsius or more across a boundary just a few kilometers wide. This sharp temperature gradient creates a visible boundary that you can see from satellites, and it also affects the weather above. Storms can intensify rapidly when they cross the Gulf Stream front, drawing energy from the temperature difference. In estuaries, where rivers meet the sea, there are convergence zones between fresh water and salt water. Fresh water is less dense than salt water, so it tends to float on top, creating a layered system. Where the two waters meet and mix, there's often a turbidity maximum, a zone where sediment suspended in the water accumulates, creating murky water even though the river water and ocean water on either side might be relatively clear. Convergence zones are also important for marine life in another way. They tend to concentrate floating material. Anything drifting in the ocean, from plankton to debris to pollutants, tends to accumulate at convergence zones where currents meet. This is why garbage patches form in the centers of ocean gyres, where converging currents carry floating plastic and other debris to a central zone where it accumulates. For seabirds and marine mammals, convergence zones are important hunting grounds. The concentration of plankton at these zones attracts fish, and the fish attract predators. Experienced fishermen know to look for convergence zones, for the visible lines on the ocean surface where different water masses meet, because that's often where the fish will be. The ocean is full of these boundaries, these zones of meeting and mixing. Some are stable, remaining in roughly the same place year-round. Others shift with the seasons, moving north in summer and south in winter, or moving with changes in wind patterns or current strength. Together they create an invisible geography in the ocean, a landscape of temperature and salinity differences that's just as real and important as the geography of the land, even though we can't see it without instruments. There's something fascinating about these invisible boundaries, these places where different worlds meet. On one side, cold Antarctic water. On the other side, warm subtropical water. In between, a mixing zone where the properties of both are present, where the character of the water is neither one nor the other, but something in between. It's a reminder that the ocean isn't uniform, isn't just blue water everywhere the same. It's a patchwork, a mosaic of different water types, each with its own history, its own journey, its own characteristics. As you drift towards sleep tonight, imagine these convergence zones. Picture the invisible boundaries in the ocean, the places where waters meet. There's no conflict in these meetings, just interaction, mixing, the creation of something new from two different sources. Let that image settle in your mind. Different waters meeting, mixing, finding balance. Let your thoughts do the same. Different ideas and worries meeting and mixing until they blend into something calmer, something more uniform, something peaceful. We've journeyed tonight through the ocean's currents, from the surface to the depths, from the tropics to the poles, from the swift flows of the Gulf Stream to the patient circulation of the Great Conveyor Belt. We've explored how winds push surface waters, how temperature and salt drive deep flows, how the moon pulls tides, and how Earth's rotation shapes everything into patterns of motion that connect every part of the ocean into one vast, interconnected system. And perhaps what's most remarkable about all of this is the constancy, the reliability, the timelessness of it. Ocean currents have been flowing for as long as there has been an ocean. The patterns we see today, the gyres and the thermohaline circulation, the Gulf Stream and the Antarctic circumpolar current, are not new. They've been operating for millions of years. Dinosaurs swam in oceans that had currents much like those we have today. The first humans to sail the seas learned to use currents that had been flowing for eons before them. This constancy, this reliability, is a gift in a world where so much changes, where technology advances and societies transform and our personal lives flow through constant change. The ocean's currents remain. The Gulf Stream still flows northward, carrying warmth from the tropics to Europe. The Great Conveyor Belt still circulates, mixing the ocean's depths. The tides still rise and fall with the moon's pull, as they always have and always will. There's comfort in this. There's peace in knowing that some things are beyond the chaos of daily life, operating on timescales so long and patterns so large that our individual concerns fade into insignificance against them. The ocean's currents don't care about your deadlines or your worries. They flow regardless, patient and eternal. Ocean currents are the circulatory system of our planet. They distribute heat from the equator toward the poles, helping to moderate Earth's climate. Without them, the tropics would be unbearably hot and the poles even colder than they are. They carry oxygen to the depths and nutrients to the surface, sustaining life throughout the ocean. They connect distant shores, carrying organisms, sediments, and even human-made objects across thousands of miles. For much of human history, we didn't understand currents. We knew they existed. Sailors felt their effects and learned to use them, but we didn't know what drove them or how they connected. Benjamin Franklin mapped the Gulf Stream, but he couldn't explain it. It took centuries of scientific study, detailed measurements of temperature and salinity and movement, complex mathematical models, to understand what we now know about how currents work. And yet, even with all our modern understanding, even with satellites measuring the ocean's surface and floats drifting through its depths, even with supercomputers modeling circulation patterns, there's still so much we don't know. The ocean keeps its secrets. Deep currents are still being discovered. The details of how water masses mix, how eddies form and dissipate, how currents respond to changing climate. These are questions scientists are still working to answer. Perhaps that's part of the ocean's magic. It's knowable enough to study, complex enough to fascinate, vast enough to remain mysterious despite all our efforts. You can spend a lifetime studying ocean currents and still find new questions to ask, new patterns to discover. But you don't need to understand all the details to appreciate the beauty of it. The elegance of a system where simple forces, wind, temperature, salt, Earth's rotation, the moon's gravity create such complex and beautiful patterns. Water flows. That's all it does. But in flowing, it shapes climate and supports life and connects the world. Tonight, as you've listened to these stories of flowing water, perhaps you've felt some of that connection. We are land creatures, yes, but we evolved from the ocean. Our bodies are mostly water. The salt concentration in our blood is not so different from seawater. In a very real sense, we carry the ocean within us. And when we rest, when we sleep, perhaps we're returning, in some small way, to that ancient source, to the rhythm and peace of water flowing. Let yourself flow now. Let your thoughts move like water, not directed, not forced, just flowing naturally from one to the next, gradually slowing, gradually becoming still. Feel the currents we've discussed tonight, the great loops of water moving through the ocean, and let your mind move with them. No particular destination, just movement, gentle and constant. The Gulf Stream flows northward through the Atlantic. The Antarctic circumpolar current circles the south. Deep water sinks and rises and sinks again. Tides flow in and out. Surface currents follow the winds. Upwelling brings nutrients from the deep. Convergence zones mark invisible boundaries. All of it together, one vast system, always moving, always in balance, always returning to itself. You are part of this system. The water you drink was once in the ocean, will be again. The air you breathe was once dissolved in seawater. The atoms in your body have flowed through the ocean more times than you could count. You are not separate from the ocean's currents. You are connected, part of the same vast circulation, the same flow. So rest now, let the currents carry you. Let the rhythm of the ocean, the slow, patient flow of water through its endless cycles, become the rhythm of your breath, your heartbeat, your thoughts slowly fading into sleep. The ocean flows on without you needing to think about it, without you needing to do anything. You can let go. You can stop holding on. The currents will continue, patient and eternal, flowing through the darkness, flowing through the light, always flowing, always constant, always there. Sleep now, as the ocean sleeps, which is to say not sleeping at all, but resting in motion, moving, and still at once, flowing, and patient, timeless and present. Let the currents carry you into dreams, into rest, into the deep quiet where thought dissolves into peace. The ocean's currents flow on. They flowed before you were born. They'll flow after you're gone. And tonight, for this moment, you can flow with them, part of something larger than yourself, something ancient and peaceful and eternal. Rest now, flow now, sleep now. The currents carry everything, including you, into the night. Good night.